So you've learned the theory of image resolution and its three elements: pixel dimensions, pixel density, and physical size. Now you're going to learn how to apply those parameters. The image size panel in Photoshop is a good example of how an image editor deals with everything that I've been talking about in regards to resolution parameters. Let's look at it. Here's a software demonstration of the dynamic relationship between physical size, pixel dimensions, and pixel density. This is the image size panel in Photoshop. This is probably the most important function in the entire Photoshop program or any other software that can edit images. You can see the file size of the image at the top, the pixel dimensions below that, the physical size, and the resolution, which I prefer to call pixel density. What does the resample box mean below that? Resample is a technical term. It means that if that box is checked, like it is now, any changes you make to the resolution or physical size settings will necessarily transform the data in the image and throw away permanently some information to accommodate the new setting. You're basically saying that you're allowing Photoshop to change the pixel dimensions to accommodate the changes you make to the two other settings. So this is an important decision. It can be undone in Photoshop, but when the image is exported outside of Photoshop, the change is frozen into the data and cannot be changed without degrading the image. This box is checked like this by default. So let's see what happens if I uncheck the box and change something. I've unchecked the box and changed the resolution from 72 to 600 pixels per inch. Unchecking it allows the other settings to adjust dynamically without changing the pixel dimensions. In order to preserve the amount of information about the image that's stored in the file, the physical size changed to preserve the information in the file. But notice the file size and the pixel dimensions have not changed at all. It's the same file with the same amount of information in it, just with different parameters. Now let's change the physical size of the image from a height of 9.5 inches to 10. The resolution changes to 571.2 pixels per inch, because if I change the physical size, those same 600 pixels per inch have to be each a little bit bigger to fit into that bigger space. So the resolution changes from 600 pixels per inch to 571. Less resolution in pixels per inch means bigger pixels, naturally. But no matter how much I play with the physical size and resolution parameters, the file size and pixel dimensions at the top will not change. But now let's check the resample box and change the resolution to 72. The physical size hasn't changed. It's still 10 inches high. But look at the pixel dimensions at the top. They had to get much smaller because the physical size is the same, but the resolution is so low. And the file size changed radically because of that. Those pixels are so much larger than before in order to fit into the same physical space, so there are far fewer of them. If you save the file now, you're discarding a tremendous amount of information. The image will be degraded significantly if you try to resize this saved file. Now let's check the resample box and change the resolution number back to 600. See how that changes the pixel dimensions shown at the top, as well as the width and height? I hope it is now clear how these three variables interact dynamically with each other, and how you can apply them to get the image you want. Scaling, in other words, changing the physical size of an image, adjusts the pixel dimensions of the image if you allow the software to resample, as you saw in the last slide. Resampling is a default in Photoshop, as you saw. As I said in the previous slide, that means that when you scale an image and save it at the new size, you are discarding information that was in the original image file. In other words, you are degrading the quality of the image. The question is just whether the amount of degradation in any particular case is within acceptable limits to you. Always keep the original source file and do any scaling with working copies. The next set of slides is about how the computer enlarges or reduces images. It's trickier than you think. It's something that is always being done on the fly almost all the time. since almost never is there a perfect mapping between the pixels established in the image and the pixels that are hardwired into the display or printer. The same algorithms are used when you resize an image in image editor software like Photoshop. I'm going to start with the simplest scenario of enlarging an image by a multiple of 100%. In this case, we're using 200%. To make an image bigger while working within the constraints of the pixel dimensions set for the image, each pixel needs to be physically bigger than the physical size of each display or printer dot. Therefore, the display or printer has to use multiples of its dots to create each image pixel. In the case of multiples of 100%, it's fairly simple. The algorithm repeats each dot horizontally and vertically a certain number of times. So where there was one single dot of color corresponding to a single pixel, for 200% resizing there is now a group of 4 dots of that same exact color, since the screen pixels are always square and have to expand in each direction. The pixels at 200% will be bigger than the original ones at 100%, and the picture might start looking grainy because of it. But you aren't really messing with the raw information that was there in the original image. You aren't actually changing, adding, or deleting colors. You're just making the pixels bigger. Now I'm going to show you what happens when you resize images at sizes that are not multiples of 100%. Resizing images outside of multiples of 100% is way more complicated than what you saw in the last slide. The illustration here is an example of resizing an image at 126%. The pixel dimensions have changed, as you can see, from 700 by 550 to 1100 by 1864. The aspect ratio of the width to the height of the image is preserved, but the problem here is that you can't have 126% of a screen or printer dot. They are hardware dots that cannot be altered. These dots of color cannot simply be replicated, like you saw on the last slide, because you're enlarging at a fractional size of 126%. Therefore, pixels need to be added and recolored in a process called interpolation to create the illusion of the original image. In this case, you'll notice that the pots of color, in other words pixels, are in groups of 4, which are now the new pixels. It has doubled all the pixels in rows and columns, just like in the last slide, but here the pixels in each group of 4 each have different colors. This is needed to simulate 126% of the original size of the pixels. The specific colors that are used to do this is a complicated algorithm, but it works as far as giving your eyes the impression of 126% of the original size. However, it permanently alters and degrades the image by adding colors that weren't there in the original. You'll especially notice it if you save this enlarged file and enlarge it again. This degradation is a key concept to remember about raster graphics, that resizing changes the information in the file such that you may see degradation of the quality of the image. So, what happens when you reduce the size of an image? The interpolation that I described on the last slide is very much necessary here as well. To make the image smaller than in the original, each pixel may need to be smaller than the physical size of each display or printer dot. But this is impossible. Even if the image has not been reduced beyond the level where pixels in the image are mapped directly to hardware pixels on the screen, a lot of interpolation or resampling is needed. To simulate the original pattern of colors and pixels, some pixels need to be deleted and the remaining ones recolored. In this case, we went from 700 by 550 pixel dimensions to 611 by 480. The aspect ratio of width to height is maintained, as always when resizing, but information has to be changed and/or discarded. Here's another illustration of interpolation in the resizing process. Here we're using multiples of 100%, in this case 200%. This is a no-brainer for the computer because all it has to do is create 4 dots of the same color for each single pixel in the original. No interpolation is needed. But now we're using a scaling factor that is not a multiple of 100%. This time it's 223%. You can't have 223% of a pixel. Therefore, interpolation is needed. Interpolation provides the illusion of being 223% bigger. Notice how there are many new colors and shades that have to be created to create the illusion of 223% scale. Downsampling reduces the number of pixels, typically to decrease file size or prepare for web use. It's important to understand that downsampling throws away information in the image, as discussed earlier. Thus, downsampling can degrade the quality of the image. Upsampling increases the number of pixels to make the image larger, using various interpolation methods to estimate new pixels. Like downsampling, upsampling may degrade the quality of the image. Interpolation methods are algorithms used to calculate and simulate new pixel values when resizing images. I talked about this in a previous video. I won't go into detail on interpolation methods here. They're quite technical. Interpolation methods are merely presented as a bullet item here to let you know that you can choose from different options in the software. You can try them out and see whether there's a difference in the quality of the image. Do not confuse the image size panel with the canvas size panel, which alters the working area without changing the size of the image that sits on the canvas. Here's a skills application challenge. Open the graphics program you most commonly use and find where in that program you control these resolution parameters. Play around with them for a while until you're comfortable manipulating them. Then go to the next video.